Hello and welcome to another exciting lecture for stats. In this lecture we will be talking about everybody's favorite topic, that is probability. We're going to talk about a bunch of different things in this set on probability, and then next week we'll finish up probability, looking at some of the more advanced things. But this week we will be looking at things like defining probability, doing a bunch of definitions for terms, sample space, events, looking at marginal, joint, and conditional probability. We'll look at the addition rule, mutually exclusive, multiplication rule, independent events, sampling with and without replacement. We'll look then at finishing up some with continuous variables and the special topic of probability at least one. And then, as I said, into next week we will talk about some of the more advanced things from probability. Before I get too far into probability, I do want to say this. I understand that some people have way more exposure to probability than others, some people have less. As a result, those with more exposure to probability, everything I'm saying here, at least the majority of stuff I'm saying here, should just come to you really quickly. People who haven't had exposure to probability, I understand that it does take a bit of extra to wrap your head around some of these rules, these probability rules. Even some of the examples I give. So I'm going to give examples of like playing cards, probabilities of drawing certain playing cards. Well, I understand that some people maybe haven't really had any experience with playing cards. When I teach stats to undergrads and I have big classes, I always ask the room who here has never experienced or even handled playing cards, and I always get one or two people that haven't experienced playing cards. For you guys, I don't expect that to be the case, but still, because of that, I tend to over-explain some things in more simplistic terms because I've just gotten into the habit of explaining things in multiple different ways so that those who haven't experienced something specific. We're going to use a couple different main things when I'm talking about it. We're going to use coin flipping, so coins, heads, tails, two different sides. I'll talk about die rolling. When I talk about die rolling, I'm always talking about a d6. That is a dice with 6 sides, a die with 6 sides. Each side has a number 1 through 6 or a number of pips, but we'll just do numbers 1 through 6. So each side has a 1 in 6 chance of coming up. And then we'll talk about decks of cards as well, where you've got 52 cards in the deck, 4 suits, 2 colors, 13 cards for each suit, 26 cards for each color. So when I talk about probability, I'll use those, and then I'll try and use simpler terms as well, like let's say you've got a bag with 10 beads in it, 8 red beads and 2 green beads. What's then your probability? But just like everything else I'm doing in here, I'm going through this quicker for you guys because you guys, I expect to already have a basic understanding of it, so we will go through it relatively quick. Okay, let's get some basic definitions down. Probability, the basic definition of probability is going to be the likelihood of an event occurring. So how likely is an event to occur? We're going to write it in this way. So it's going to be the P and then whatever it is we're interested in. So if we're interested in A, if we're interested in B, if we're interested in X, the probability of that event occurring is how we're going to write it. And then we'll write it out like that. It will range from 0 to 1. You cannot have a negative probability and you cannot have a probability greater than 1. And probabilities can then be expressed as a proportion, so that decimal place. It can be expressed as a fraction, and it can even be expressed as a percent, which would be, in this case, 30%. So if you have this event that has a 0.3 chance of happening, it has a 3 in 10 chance of happening, it has a 30% chance of happening. These are all the different ways that it could be written as. Now we need a few other definitions to go here. our sample space is basically going to be all possible outcomes. So those 3 examples I gave just a minute ago, the sample space is for a coin is going to be the 2 possible outcomes, heads or tails. The sample space for a deck of cards is going to be the 52 possible outcomes. The sample space for a die with 6 sides is going to be the 6 possible outcomes. Sample space, very simple term, it's all possible outcomes. Then we have event. So event is whatever we're interested in occurring, or whatever we're interested in measuring. So it's an outcome or a set of outcomes. It's not necessarily just one. A set of outcomes within the sample space that forms a subset of the sample space of interest. So one example would be if we roll a die, the event might be an even number. The event, which would then be 2, 4, or 6. The event might be just 2. The event might be something greater than 3. So in that case, we've got 4, 5, and 6. The event can be one thing, can be multiple things, but it has to be within the sample space. So it has to be a possible outcome, and that forms a subset of the sample space. The possibility could be if the event is rolling a number, so 1 through 6. So then the probability of it occurring is 100% because it's all possible things within the sample space. So we talked about event there. Now let's talk about the complement of an event. It's often referred to as not the event. So if the probability of A is the event, the complement is the probability of not A. There's many different ways to write this. You can write it as not A, the squiggly and then A, an A with a bar over it that looks like the mean. All of these are different ways to write it. You'll probably see me when doing probability write it like this last one with the bar over the top of it, so the probability of not A occurring. So let's look now at an example when playing with cards. If you're looking to at the deck, drawing a jack is the event. So the probability of getting a jack, and it equals 4 out of 52 because there are 52 cards. The probability of getting a not jack, so putting the bar over it, is going to then be equal to 48 out of 52 because there are 48 cards that are not a jack. One thing to note here is that the probability of an event added to the probability of its complement always adds up to equal 1. That is because they take up all possible things in the sample space. We'll talk about that again in just a little bit, but the term here would be they're exhaustive, meaning all possible events are exhausted, all possible outcomes are exhausted in this, so the total comes out to 1. You can't draw a card from a deck that is both not a jack and not a jack. A better way to say that is, if you draw a card from a deck, you're going to, with 100% probability, get either a jack or not a jack. Next term we're going to define here is mutually exclusive. So mutually exclusive is when we look at the events that do not have any outcome in common. So there's no overlap between events. When we're looking at this, we're looking at whenever you have an example where they're between 2 different events, there is no overlap. So there's no outcomes in common between the 2 different events. An example would be spades and hearts are mutually exclusive, 2 different types of cards. With rolling a die, evens and odds are mutually exclusive because you can't have both. However, kings and clubs are not mutually exclusive because in the deck there is a king of clubs. And if you said, what's the probability? The probability the 2 events are getting a 3 on a die and getting an odd number. Well, they're not mutually exclusive because the 3 is also odd. There is overlap between the events. And here it needs to be noted that an event and its complement are always mutually exclusive. So they're always mutually exclusive, they're always exhaustive, which we'll get to in a little bit, and they always add up to 1. A good question to put on an exam. An event and its complement are what? And it's all of those. Let's look at a visual way to do mutually exclusive. So first you've got event A, you've got event B. There's no overlap between them. They're mutually exclusive. And instead you can have them when they're not mutually exclusive, when you've got event A and event B, and what you end up with is this area that's both A and B. So in that case, they are not mutually exclusive. Another thing I said I'd talk about is exhaustive. Exhaustive, and I already said this, but it is when an event contains all outcomes in the sample space. So when we look at exhaustive, let's give some examples. Red cards and black cards are exhaustive. All possible cards fit into that. We're talking about a standard deck of cards, no jokers. So all cards in the deck are either red cards or black cards. However, hearts and clubs are not exhaustive because then you've still got spades and diamonds. That only takes up half the cards. If we looked at rolling a die, so things that would be exhaustive, evens and odds are exhaustive. And if you did 6 different events, the event A, event of rolling a 1, event of rolling a 2, event of rolling a 3, event of rolling a 4, event of rolling a 5, and event of rolling a 6, those events together would be exhaustive because it takes up all possible outcomes. And as I'd already said, an event and its complement are always exhaustive. So when we looked up just an event and its complement, they're mutually exclusive, they're exhaustive, and they add up to 1. Next thing we're going to talk about is partition, and that is when events are both mutually exclusive and exhaustive, they form a partition of the sample space. What I'm talking about here is basically looking at if we have diamonds, hearts, spades, clubs, we have all of them, they're all mutually exclusive, so you can only be in one of these events. And they're exhaustive. They take up all the possible events. We say that these form a partition. The probabilities of events that form a partition must sum up to 1. That is because they're exhaustive and mutually exclusive. And just like all the other things, an event and its complement form a partition. So now you have 4 different examples of things that I could ask for an event and its complement. They form a partition, they're mutually exclusive, they're exhaustive, and they add up to 1. Let's actually get now into probability now that we've defined a whole bunch of things. So now we've got the probability of an event occurring. So as I said before, that's how we would write it. We'd write it with a P, and then whatever we're interested in. Let's say we're interested in X, and then we have it equaling like that. To calculate out that, the formula is the number of occurrences in the event. So the number of outcomes in the event divided by n. So if we were looking at the probability, and let me erase this, and the probability of getting a even number on a die roll. The number of even on the die roll would be 2, 4, and 6. So it would be 3 total possible outcomes for our event divided by the total number of outcomes. There are 6 sides, there are 6 total outcomes. So we end up with 1/2 or 0.5. Let's say we wanted to factor out another example. We wanted to select a card from a standard deck of cards. What's the probability of selecting a club? Well, there are 13 clubs, so the number of outcomes in our event is 13. There are 52 cards, So it's 13 out of 52, or 1 out of 4 if we reduced it, or 0.25. So the probability of drawing a club is 0.25, 25%, and that's because it's 13 possible clubs out of 52 possible cards. Now we're going to look at an example and kind of look at a probability chart or a probability table. So we're going to start with this example here of we have 800 individuals. They're categorized along two dimensions: self-esteem, low versus high, and depression, low versus high. One way, this is one way to write it. One way to write it is another way to write it would be we would put an S for high and a not S for low, and a D for high and a not D for low. That's one way to write it to make it shorter. Why would you do that? Well, if you're writing this out, instead of writing the probability of having high self-esteem and high depression, you could then say the probability of S and D. And how I did that is just I did the probability for S. The reason I did S there because it's self-esteem, so that person has high self-esteem. The not S means not high self-esteem. D, high depression, not D, not high depression. I'm going to keep it as it is with the high and low, but one way I would write it is instead of with high and low like this would be with the event and not event to keep it consistent with probability. Now we're going to talk about a marginal probability. So a marginal probability, also called a simple probability or a basic probability, it is a probability that doesn't involve other events. So it's when we're only looking at one thing, one event. Now the event can have multiple outcomes. So again, it could be like the event of drawing a club from a deck. So it's got multiple outcomes, but it's looked at as independent of other events. We're not looking at the other events. So if I was saying drawing 2 cards out, or drawing a club and rolling a 3 on a die, that type of thing, we're just concerned with the one event, not with other events. So other events, they may be present, but they're ignored. In our example we've got going here, depression and self-esteem, the 2 events that are going on are, does the person have high self-esteem and does the person have high depression? When we're talking about a marginal, we're just looking at one of those individually, just the depression or just the self-esteem. And this uses that formula we already used, that the probability of that event occurring is equal to the number in that event divided by the total number of occurrences or possibilities. Back to our example here then, let's look at each of these. Let's factor each of these out and figure them out when we are now dealing with the different marginal probabilities. So first we're just looking at low depression. So it's equal to essentially just depression. So we're looking at low depression. So we're looking at low, but we're looking at total because it is a marginal probability. So we're looking at the margins. The margins, the totals here and here is what we're looking at. So we're ignoring self-esteem for now, and we're just looking at low depression. So it's going to be 600. There's 600 that have low depression divided by 800 total, or 0.75. And we would write that right here. Now we're looking at high depression, so all the way over here to the marginal for high depression, we've got 200 divided by our grand total again, 800, or 0.25. So we've got 0.25 here. Next one we're going to look at now is low self-esteem. So we are looking at self-esteem, but we are looking at the marginals. So we're going to look at this 300 here. So it's going to be 300 divided by our total of 800. This is equal to 0.375. And the final one is high self-esteem. So we're going down there. We've got our 500 divided by 800, and we get 0.625. Now, there's some other things we can fill out here. First of all, in this total in the bottom right, it's 800 divided by 800, so it's going to be equal to 1. I should just point out here some things that you can figure out that will help you later when you're dealing with these types of charts. First off, the 600 here plus the 200 is going to be equal to 800 from down here. The 300 over here for low self-esteem plus the 500 for high self-esteem also equals 800. You can also do this for your probabilities. The 0.75 under low depression added to the 0.25 from high depression equals the 1.00, as well as the 0.375 for low self-esteem added the 0.625 for high self-esteem also equals 1.00. So these marginal probabilities, you can figure them out in multiple different ways, but the way that you figure out each one individually is by dividing the number for that in the margin by the total. Next, we'll talk about joint probabilities. So joint probabilities are going to take this one step farther. Now we're looking at the probability of events occurring together. And the way we say this is the probability of A and B. So A and B is a joint probability. You might sometimes see it like this is over here on the right, A comma B, but you're almost always going to see it like this, probability of A and B. And what is the formula for this? Very similar to the marginal probability, as in it's the number of occurrences for that event divided by your grand total. Well, now we're looking at the number of occurrences where A and B are occurring divided by your grand total. So let's go back to that chart again. Now we're going to look at the joint probabilities. So again, we had, I'm just going to write some things in here, 0.75 here, 0.25 here, 1.00 here, 0.375 here, and 0.625 here. So that was our marginal probabilities. Now we're actually going to do the joint probabilities. So this first one here, we're looking at low depression, and low self-esteem. So we're going to find the intersection of those, the joint intersection of those, which is 110, and do 110 now divided by our grand total of 800. And that equals 0.1375. Next, we're going to look at high depression and low self-esteem, and that is 190. So we're doing 190 divided by 800. And this is 0.2375. Next is low depression again up here, but high self-esteem. And this is going to be 490. So 490 divided by 800. And we get 0.6125. And then finally, we have high depression, high self-esteem. We get a total of 10. So we have 10 divided by 800, and we get a total of 0.0125. Let me actually write these over here. Now, I'm going to point out some more things that are going on with this table that are interesting. So I told you before how if we look at just depression, how low depression 600 plus high depression 200 equals 800. And how low self-esteem 300 and high self-esteem 500 equals 800. But also how the probability is 0.75 for low depression and 0.25 for high depression equaled to 1 total. Well, now you can actually do some more math here. First off, if we looked at just low depression but looked at it within self-esteem, you've got this 0.1375 and 0.6125. If you add those together, you actually get 0.75. So add the two low depression numbers, you get the total. Down below it for the high depression, the 0.2375 and the 0.0125, you add those together and you get the 0.25. And the same works going down for self-esteem. So if we looked at low self-esteem, 0.1375 and the 0.2375, we get 0.375 if you add those together. If you add up 0.6125 for high self-esteem, low depression, and 0.0125 for high self-esteem, high depression, you get 0.625. Plus, if you add all four of these numbers together, you get 1.00. So there's different ways to figure out the numbers. If you've got some of them, you can figure out others from them. And you can double check your work. So this is that table. This is what's called a joint probability table. You can do it the way I did it on the previous slide and have the frequency table there with the probability table, or you can just do the joint probability table. Depends on what's asked for in the homework and the exam. If it's asked for a frequency table and a joint probability table, then you should put both. If it's just asking for a joint probability table, then you just need to put what's on this slide. Next thing I'm going to talk about is one step more complex, and that is what's called a conditional probability. So a conditional probability is the probability of an event occurring given that another event has already occurred, or given that another event is occurring as well. And basically, this is going to be a ratio of joint to marginal probabilities. So it's going to be a ratio of joint to marginal frequencies or joint to marginal probabilities. A couple different ways to have this written out, and the way it's written is what you see over here, and this is how you would say this, is it's the probability of A given B. And you can do it as a frequency or a probability. So the frequencies that you see here, it basically, this middle one, they end up canceling out. So this one I don't recommend using. I recommend either using this one where you use frequencies, or this one where you use probabilities. I'll give some examples of that on the next slide, but just pointing out here that how you calculate this and how you word this is the probability of A given B. What that means is the probability that A occurs given that B occurs. And it's a ratio of the events occurring together divided by the event given. So another way to do that is, let me just do probability of B given A. This is going to be equal to the probability of A and B, which is also the same thing as the probability of B and A. They're the same thing because it's a joint probability. You could say A and B or B and A. It becomes out to the same thing. But then we're dividing by the given, so the probability of A. So you see down here, when we go over to this one on the right, for our formula. It's the probability of A given B. So it's the probability of A and B, the joint probability of the two events, divided by the probability of the given event. So it's given B. So it's the B is here because it's divided by the probability of the given event. That's one thing a lot of people confuse. That's why I'm going over it in detail, is because this is something that people do get wrong, is if I change it from probability of A given B to probability of B given A, you would then have to divide by something different. You have to divide by what it's given, not what is just whatever one you choose. You have to divide by the one that's given. Let me give some examples of that. So we've got both the up at the top, we've got the frequency table. Down at the bottom, we've got the probability table. Let's actually calculate out the probability of low depression given low self-esteem. So this is the probability that someone has low depression given that they have low self-esteem. So we've got a event occurring given that another event has occurred or is occurring. So what we're going to do then is it's going to be equal to the AND of the two of these. So the low depression and low self-esteem, which is how you get this. So the number of low depression and low self-esteem. We've got low depression, low self-esteem. Our number is 110. So it's going to be equal to 110. And then we're going to divide by what is after the given. So the total for low self-esteem. So we're going to be dividing by the total for low self-esteem. Again, if it's just you've got this here, the number, this is just a marginal frequency, marginal probability when we get down to the bottom. So it's 110 divided by 300. 110 divided by 300 is equal to 0.37. So the probability of having low depression given you have low self-esteem is 0.37. It is a conditional probability of basically of low self-esteem or low depression given low self-esteem is happening as well. You can do this with probabilities as well. You get the same answer. So now we've got low depression and low self-esteem, but instead of doing numbers, which is a frequency, we're doing probability. So we use the probability table. The probability of low depression and low self-esteem is this 0.1375 divided by the probability of low self-esteem, which again is a marginal probability because it's a simple marginal probability. So that's the 0.375. And the answer we get is the same thing, 0.37. So that would be how you would do a conditional probability. And I could do other conditional probabilities. Well, what's the probability of, let me just do a quick one here so that and it's not even related to this. What's the probability of drawing a or even rolling a 3 given you've rollen a 5 before? Well, I'll actually come back to that one. I'm not going to write it on this slide because that's an interesting thing that comes up when you've got events that are with replacement and without replacement. So let me just come back to that. Next thing we'll talk about is what's called the addition rule in probability. So we talked before about probability of A and B. The addition rule, and don't get confused here, addition does not mean and here, addition means or. We're going to use the addition rule in events because of just a principle of probability of things end up getting counted twice if we don't use this addition rule. So the probability of A or B is also called the union of events, which is when you're looking at the probability of one event occurring or another event occurring. So on that previous one, what's the probability that someone has low self-esteem or low depression? Not necessarily both, but they could have both. However, we use this formula. We use the simple probability, the marginal probability of A, the simple marginal probability of B, but we actually subtract off the joint probability of A and B. Why do we do that? Because otherwise A and B would be counted twice. If you're counting the probability of A occurring here, you're counting the probability of B occurring here. What ends up occurring is when you count the probability of A, which we'll put in green, and B, which we'll put in purple, this section in the middle, this A and B, is counted both times. So since it's counted twice, you need to subtract that off to keep it from being counted twice. A good example of that would be, let's say we counted the probability of, and I'll see what I've got coming up, but let's say we wanted to know the probability of rolling a number greater than 3 or the probability of rolling an even. Well, we need to do the probability of rolling greater than 3 plus the probability of rolling even minus the probability of rolling both greater than 3 and even. So what's the probability of rolling greater than 3? Well, there's, let's put it over here, 1, 2, 3, 4, 5, 6 are our numbers. The probability of rolling greater than 3 is going to be equal to, you've got a 4, a 5, and a 6 are all greater than 3. There's 6 total sides, so it's 3 possible outcomes, 6 total sides, so it's 0.5, half. Probability of rolling an even. Well, you've got a 2, a 4, and a 6. Again, it's 3 out of 6, or 0.5. If we didn't take off this, and let me use blue here, if we didn't take off the probability of rolling greater than 3 and the probability of rolling even, we'd add these together and we'd get 1, which means that the probability here of rolling greater than 3 or even, we would say is 1. However, there's the possibility of drawing a 1, or rolling a 1, or rolling a 3. The 1 and the 3 didn't come up in either of our scenarios, so there's actually chances of not getting greater than 3 or an even. So we can't just do the add the two together. We now have to take off the probability of rolling greater than 3 and even. This is the joint. This is where both are occurring. So in this instance, let's use purple here, where both are occurring, greater than 3 and even. So the 4 is greater than 3 and is even, and the 6 is greater than 3 and is even. So in this case, we've got, it would be 2 divided by 6, or 1/3. And what we end up with here is we end up with, another way to write it, 3 divided by 6 plus 3 divided by 6 minus 1 divided by 3, or 2 divided by 6. Let's just do 2 divided by 6 there. We end up with 4 divided by 6 as our total, or 0.67. So the probability of rolling greater than a 3 or an even is 0.67, not 1. Looking at another example of that, so now what's the probability of drawing a heart or a king from a standard deck of playing cards? So we need to do the probability of drawing a heart plus the probability of drawing a king minus the probability of drawing a heart and a king. Probability of drawing a heart is, there are 13 hearts. There are 52 cards, so it's 13 out of 52. Probability of drawing a king is there's 4 kings, so it's 4 out of 52. The probability of drawing a heart and a king, again, this is when there's an overlap, so all instances of hearts and kings, there is 1 divided by 52. So it's going to be 13 out of 52 plus 4 out of 52 minus 1 out of 52, or 16 out of 52. And if you wanted to convert that over to decimal, you get 0.31. Let's just look at some other things like mutually exclusive. We kind of talked about mutually exclusive, but mutually exclusive again is if events that can't occur simultaneously, they are mutually exclusive. Occurrence of one event means the other event cannot occur. So you can't have both a even roll and an odd roll. There is no time where they're going to be overlap with those two because they are mutually exclusive. Having no events in common are mutually exclusive. So when we're dealing with this though, why is this important? Because when events are mutually exclusive, the probability of A and B, the probability of them occurring together is going to equal 0. So an example here would be the probability of drawing a heart and a black card at the same time. Well, they have nothing in common, so the probability of the two together is equal to 0. Where does that come into play, or when does that come into play? Well, it comes into play in our addition rule we were just talking about. That is, with the addition rule and mutually exclusive, it ends up coming out to be that we don't even need to do that last part. So let's do this real quick. So addition rule, probability of drawing a heart, if I can write an H correct, probability of drawing a heart plus the probability of drawing a spade minus the probability of drawing a heart and a spade. Well, the probability of drawing a heart is 13 out of 52. The probability of drawing a spade is 13 out of 52. The probability of drawing a heart and a spade is 0. There is no cards that are hearts and spades. Therefore, we don't even have to do the joint probability as part of our addition rule when there is no overlap, when the events are mutually exclusive. You can just do the event like that. Because again, if your events are mutually exclusive, there is no overlap, you don't even have to worry about subtracting the joint probability. So we end up with 26 out of 52, or 0.5. Let's do a couple examples real quick. So what's the probability of getting a 3 or a club? Probability of a 3, or just going to erase part of that, 3 or club is going to be equal to the probability of getting a 3 plus the probability of getting a club minus the probability of getting a 3 and a club. So 4 out of 52 plus 13 out of 52 minus 1 out of 52, because there is one 3 that's a club, equals, again, 16 out of 52. What's the probability of getting a 4 or a 10? This is going to be equal to the probability of getting a 4 plus the probability of getting a 10, and I don't even need to subtract off 4 and 10 because it is equal to 0. If I wanted to put it there, I could, but you don't have to because they are mutually exclusive. There are no cards that are both 4 and 10, so we are just left with 4 out of 52 plus 4 out of 52, or 8 out of 52. Hope that's enough examples. Now let's add in another rule. So we added in the addition rule before. Let's look at the multiplication rule now. And this is going to be another way to calculate A and B. This is another way to calculate the intersection of events. Why is this important? Well, you don't always necessarily have access to the same information we had earlier, so you can't just do a very simple all occurrences of them happening together divided by the total number of occurrences. You sometimes are only given specific things, not to mention something that's going to come up in a couple slides, which is we're going to be talking about, or even in the next slide, we're going to be talking about with replacement and without replacement. What do I mean by that are events tied to each other, or are events independent? We'll come back to that though. So the multiplication rule basically states that the probability of A times the probability of B given A equals the probability of A and B occurring. And also the probability of B times the probability of A given B, depending on how you're ordering it. But this is how the multiplication rule works. I will have an example of it in just a couple slides, and we will look at how that works. Actually, let's look at that on the next slide. So let's use the multiplication rule. So now we're looking at the probability of getting a heart and a red card, but the point here is and then a red card. So we're not just looking at getting one draw that's both of these. We're now looking at two draws. This is the first draw, the heart, and then the second draw is the red card. And an important note here is without replacement. I will talk about this a little bit more in just a minute, but without replacement means after you draw the first card out, you do not put it back in the deck before you draw the second card out. So you draw the first card out, but not the second. So this is going to be equal to the probability of drawing a heart times the probability of drawing a red card given that a heart was drawn on the first draw. How does that work out? Well, let's look at that let's use this example. So the probability of drawing a heart is, there are 13 out of 52, or 0.25. So the probability of drawing a heart is 0.25. But then we're going to multiply that by the probability of drawing a red card given a heart has already been drawn out. Well, how many red cards are there? Typically, there would be 26. But we've already drawn a heart out. So because we've already drawn a heart out, let's just look at this, or we'll even just look at it this way. I'll explain it this way. The first card you drew out was a heart. So our given here is you drew a heart. So the probability of drawing a red card given that you drew a heart. How many cards are there total that are red if one of the hearts is gone? Well, there's not 26, there's 25 left. There's 25 red cards because we drew a heart out already and didn't put it back in. How many cards are there total? Well, normally you would have 52 cards, but we drew a heart out, we didn't put it back in, so now there are only 51 cards. So we get 25 divided by 51 for that, or 0.49. And then we multiply those together, that 0.49 times 0.25, and we get 0.1225. We'll just do 0.12. So the probability of drawing a heart and then a red card without replacement is 0.12. So as you can see, these probabilities are starting to get a little bit more complex here. Let's look at events as independent. So we're throwing out another term here, independent. Independent events are where the occurrence of one event does not affect the occurrence of another event. This is basically when your conditional probability equals a marginal probability. So what am I saying here? Your probability of A given B is equal to your probability of A. If events are independent, it doesn't matter that B has occurred. The probability of A is going to stay the same regardless of if B has occurred. And the same here, probability of B given an A, it doesn't matter if A has occurred. It's independent. The one event does not affect the occurrence of the other event, so the probability of B given A is the same as the probability of B. Let me actually use an example of that. Example would be flipping a fair coin. So fair coin, it has two sides. The probability of getting a heads is the same regardless of what's occurred before. Let's look at, so the probability of getting a heads given that a tails has occurred. Well, the probability of getting a heads is not going to change because that tails occurred. So it just equals the probability of getting a heads, which equals 0.5. Getting that tail did not affect future probabilities. It's actually what's called the gambler's fallacy. If you fall into that, or if you think about it, if you want to think about it or look at it deeper, that is, the gambler's fallacy is the belief that independent events are not independent. If I flip a coin 5 times and I get heads every time, and I go to flip that coin again, what's my probability of getting a heads? 50%. It doesn't become lower because I've gotten a heads a bunch of times. So when people are rolling dice or things like that, and they say, well, this number is due, that is the gambler's fallacy, because the probability doesn't change from one occurrence to another in independent events. So this gets us back to what I was talking about a minute ago, and that's with and without replacement. And I'm going to define those a little bit more now. So sampling with replacement is when, after one outcome, you reset the sample space. So when an outcome occurs, the sample space is reset, so the next selection essentially has the same sample space as the first event did. These events are independent, meaning the probability of getting something on the second event is the same as the probability of getting something on the first event because the sample space was reset. So if you've got a deck of cards, you draw out one card. You draw out a heart, let's say. Then you put it back in the deck. What's your probability of drawing a heart on the next card? It's the exact same as it was of drawing a heart on the first card because there's now still 13 out of 52 cards in the deck that are hearts. However, the other side is sampling without replacement. And this is where the sample space is not reset. When you're drawing cards out, you don't put it back in. You're drawing beads out of a bag, you don't put them back in. These events are dependent. These events are not independent. And this is where you get into different types of probabilities, and you'll see this on your homework, where if you're sampling with replacement, your probabilities are going to stay the same. If you're sampling without replacement, after each successive iteration, so if you do 3 things in a row, drawing 3 cards out of a deck, that type of thing, without replacement, then your probabilities are going to change for each successive event. Just give an example of the probability of drawing 3 red cards. So the probability of 3 red, also equal to the probability of red and red and red. Meaning you draw a card, it's red, you draw a card, it's red, you draw a card, it's red. What's the probability of this? With replacement, the probability of drawing a red card is equal to, so it would be, the first one would be equal to 26 out of 52. And using the multiplication rule, we're going to multiply each of these. So using the multiplication rule, we multiply them. The probability of, so this would be the probability of a red. The middle one would be the probability of a red given that you've drawn a red. And then finally, the probability of a red given that you've drawn two reds. So we're going to multiply each of those. With replacement, we get 26 out of 52 because the 26 out of 52 chance of getting a red card. You put that card back in. So your probability of drawing a red given a red is still 26 out of 52 because you've reset the sample space. And finally, the probability of drawing a red given that you've drawn two reds is 26 out of 52. However, with replacement, or sorry, without replacement, down here at the bottom, the probability changes some. So the probability of drawing a red card is still 26 out of 52. If I can write correct. 26 out of 52. However, the probability of drawing a red card given that you've already drawn a red card, well, now one of the red cards is gone. You didn't replace it. So there's only 25 red cards left. And there isn't 52 cards left, there's 51. And now the probability of drawing a red card given that you've drawn two red cards. So we're now doing the drawing a red card given that you've drawn two reds. Well, two red cards are gone, so there's only 24 red cards left. And two cards are gone from the deck, so there's only 50 cards. So as you can see here, the probabilities are going to be slightly different when you're doing with and without replacement. The likelihood of this happening is slightly lower than the likelihood of this one happening, because every time you draw a card out, you're successively reducing the likelihood of the next event occurring. And you're going to have to do something like that on your homework. So let's look at the multiplication rule in independent events. So if events are independent, again, we were looking at it like that. I kind of just did this on the last slide. Well, if when they're independent, if the probability of A given B here, or A given B here is equal to the probability of A, or the probability of B given A is equal to the probability of B, then the end result is it's just the probability of A times the probability of B. You don't have to do these givens, because if they're independent, you've got with replacement, it isn't, the givens don't matter. Let's look at an example of that real quick. So the probability of with replacement, drawing a heart and then a red card. So we're going to have the probability of a heart and red. Normally that would be equal to the probability of a heart times the probability of a red card given a heart. But we did with replacement, so they're independent, so it's actually going to be the probability of a heart times the probability of a red. If we wanted to figure that out, probability of a heart is 0.25, 13 out of 52. The probability of a red is 0.5, or 26 out of 52, and you get 0.125. Let's look at, again, more examples. I'm just going to do these examples really quick. We'll do with and without replacement for getting 3 aces. So with replacement, it's 4 out of 52 times 4 out of 52 times 4 out of 52, Without replacement, though, it's 4 out of 52 times 3 out of 51, times 2 out of 50. Again, because here you've already drawn 1 ace out, here you've drawn 2 aces out. I used the example of that a few slides ago, so I'm not going to spend more time on this slide than that. There is a rule to be taken into account when we talk about without replacement. That is that when we're sampling without replacement from a relatively large population, we actually treat the events as independent. Why do we do that? Let's say a university has 30,000 students, 15,000 male and 15,000 female. If you randomly select 2 students without replacement, so the first student can't be selected again, what's the probability that they're both males? So you draw the first one out, and it's technically 15,000 out of 30,000. The second one is this 14,999 divided by 29,999. We treat them as independent, though, because if you factor it out with rounding, this 15,000 divided by 30,000 times 14,999 divided by 20,999, you get this same number. So we just use the multiplication rule for independent events when sample sizes are sufficiently large. And this is why when dealing with probability and we're dealing with large samples, we consider them events to be independent even if technically they're not independent. Technically, after you draw the first male out, if that person doesn't have a chance of being selected again, then technically they're dependent events, but probability-wise, due to rounding, they're going to come out as the same thing as independent. Okay, the last main thing we're going to look at here, we're just going to look at a couple other little things, but the last main thing we're going to look at is the probability of at least one. So the probability of at least one is a special instance of probabilities. Why is it a special instance? That's because we actually get to this probability by going in a reverse direction. So let's say we had the probability of drawing at least one ace. How would we figure that out? Well, we know first off that because events are exhaustive, that the probability of all events occurring must sum up to 1. So all events possible, the probability of getting 0 aces, the probability of getting 1 ace, the probability of getting 2 aces, the probability of getting 3 aces, depending on how many times we're drawing, the probability of that occurring, if you add up all of those probabilities, then you get to 1. However, when we're doing the probability of at least 1, we can actually use a special rule. That special rule is that when we know that these add up to 1, so the probability of getting, let's say we were drawing 3 aces, or we were drawing 3 times. So we'll ignore the ellipse here. Let's say we're drawing 3 times here. The probability of getting 1 ace, or the probability of getting 2 aces, or the probability of getting 3 aces is equal to the probability of getting 1 ace plus the probability of 2 plus the probability of 3. So the probability of getting exactly 1, exactly 2, and exactly 3. If you add all of these together, what you actually get is 1 minus the probability of getting 0 aces. Meaning, you add these 3 together, we go back up to this rule at the top. This important rule at the top, that the sum of all probabilities is 1. Well, the sum of all of the opportunities of getting an ace here would be equal to 1 minus the probability of getting 0 aces. Because you can either get 0 aces as an opportunity, as an outcome, or you get at least 1. Again, They're mutually exclusive. You can't have at least one ace and 0 aces. They're exhaustive. You have to have one or the other of these. In a sense, the probability of getting 0 is the complement of the probability of getting at least one. Therefore, an easier way to calculate the probability of at least one, instead of calculating the probability of getting exactly one ace, and the probability of getting 2 aces, and the probability of getting 3 aces, instead of calculating those all out, adding all of those together, what you can actually do is calculate out the probability of getting 0 aces, and just take that away from 1, and you get the probability of at least 1. Let me show that on the next slide. I'll give an example of that. If you draw 3 cards from a deck without replacement, from a standard deck of playing cards with the probability of getting at least one ace. So this is what I've been saying. So the probability of at least one ace, it's equal to the probability of getting 1 ace, or getting 2 aces, or getting 3 aces. One of the 3 of those occurring. But an easier way to factor it out, instead of calculating all of that, is to factor out the probability of getting 0 aces. And then just taking 1, subtract that. So 1 minus the probability of 0 aces. Well, how would you factor that out? Well, we're doing without replacement, but what's the probability of not getting an ace on your first draw? Well, there's 48 cards in the deck that are not an ace. There are 52 cards. Then your second draw. There are now 47 cards left in the deck that are not an ace, and there are 51 total cards. And then finally there are 46 cards, and there are 50, so this is the probability of getting not an ace, times the probability of getting not an ace given not an ace has been drawn, and then the probability of not an ace given 2 not aces. And if you factor all this out, you end up getting this is equal to 0.7826, but you do 1 minus that, and you end up with a score of 0.22, which is this number here. So, in a sense, the easiest way to get the probability of at least one. So when I ask for that on the homework, when I ask for that on the exam, probability of at least one. Instead of calculating out all the different possible outcomes with getting aces, instead factor out the probability of getting no aces and take 1 minus that. Now I'm going to finish up here with just kind of a preview of what we're going to talk about next week. So up to this point we've been talking about static variables or discontinuous variables. You can't have half of a playing card. You can't have half of a die roll. However, in real life most variables are continuous. So the way we would do that is when we do continuous variables, we calculate area under the curve for a range of scores. So we're going to, instead of calculating it straight out, we're going to look at it like those z-scores we just did last week. First, you convert your x-scores to z-scores, and then you can use the z-table to calculate out a probability. Let's look at an example of that. So assume test scores are normally distributed. Again, you have to have that assumption of normal distribution. We've got a mean of 10, standard deviation of 2. What's the probability of scoring a 13 or higher? Well, first thing we have to do is convert it to a z-score. So 13 minus 10 divided by the standard deviation of 2, we get a z-score of 1.5. Well, now what is the probability of getting that score or higher? That is going to be what's in gray here, and that is the area above the curve. So above that number area under the curve above that number, and that area is 0.0668, so the probability of getting a 13 or higher is 0.0668 or 6.68%. And this is the first step, and we'll like I said, we'll continue this next week, but this is the first step towards getting to inferential statistics. Because in inferential statistics, we look at these continuous variables and we look at probability in this way. Let's even look at using both rules in a problem, both the addition and the multiplication rule. This is, again, we're doing a little bit of a preview of what's going to occur next week. This isn't necessarily for the continuous, this is just in general for probability. But let's say you flip a fair coin 4 times, what's the probability of getting exactly 2 heads? Well, one way you can figure this out is to figure out all the possible outcomes that have 2 heads. And then you just do all the possible outcomes that have 2 heads, and you do that divided by all the possible outcomes, and you get your probability. Another way to do it would be, and as we're going to see on the next slide, when you take all those possible outcomes and do the multiplication rule and then put in the addition rule. So first, the probability of getting a head, a tail, and a tail is equal to 0.0625. The probability of getting a head, and a tail is 0.0625. Actually, the probability on all of these outcomes is 0.0625. But if you add all of them together, you get 0.3750. And when we're looking at this, this is basically using both of them together, both the addition and the multiplication. However, this is a very time-consuming and difficult way to do it. I do not recommend doing it this way. I'm only showing this as an example of how you could use them together. And that is because, in this case, you've only got so many possible outcomes. You've only got all of the different possible outcomes for what you could get here. I forget exactly how many outcomes there are here. Let me actually figure that out real quick. There's actually 6 possible outcomes there. So when we've got 6, there's 16 different outcomes you can have for this. So there's only 16 different outcomes you can have. So when you're looking at flipping a coin 4 times, you only have to figure out the 16 different outcomes. And how I was figuring that out is there's 6 outcomes that get 2 heads. There's 16 total. That's equal to 0.375. However, what if you want to flip a coin 6 times, 7 times, 10 times, 20 times? Figuring out all the possible outcomes and figuring out all the possible times where you've got exactly 2, exactly 3, exactly 5 heads, that type of thing, that is difficult and time consuming. And that is what leads us into the next slide, which is the binomial distribution. And this is a distribution where you're looking at possible outcomes when you have exactly 2 possible outcomes. And you can stretch that way beyond that, because anytime you're looking at an event and its complement, you've got exactly 2 outcomes. Either the event can occur or its complement can occur. Even if you're talking about rolling a die and you've got 6 die faces, when we're talking about, let's say, the probability of rolling a 3, well, you've got 2 possible outcomes, rolling a 3 or not rolling a 3. So you can use the binomial distribution for that. And I'm going to put it up on the screen and you can look at this, but we're not going to talk about it now. It looks pretty complex, it's pretty in-depth. That is because next week we will look at this in much more detail, and this is basically the preview of what we're going to look at next week. This and some other higher order probabilities that are going to lead us into the ability to do inferential statistics. All right, that lecture went a little bit longer than I intended, but hopefully you watched it. Hopefully you understood it. If you have any questions, send me an email, ask in the discussion board. Other than that, thanks. Come on back.